Now this proof incorporates a couple of new ideas, but before we look at those, I guess we'd better see what the question is. PQRS is a parallelogram. M is the midpoint of PS and Rx equals twice XP. We're also told that vector RQ is small a and the vector RS is the vector small b. We're required to show that Q, X and M are 3 points on a straight line. Now you may be looking at this wondering how on earth are we going to prove that Q, X and M are on a straight line. It certainly doesn't look easy. Well, it turns out to be really simple in principle, although you need to be pretty good with fractions. First, we need to prove that QX is parallel to XM, and we do this by showing that vector QX is a multiple of vector XM, because you'll remember that if we multiply a vector by a scalar, a simple number, we get a vector that's parallel to the vector we started with, but just longer or shorter. Secondly, we say that if QX is parallel to XM, then Q, X and M must lie on a straight line as they both pass through the point X. There's no other way it could be. So now we have a clue as to how to begin. We need to find the vectors QX and XM in terms of vector small a and vector small b, and show that one is a simple multiple of the other. So let's give it a go. We need to find a high road from Q to X. As this is a parallelogram, vector QP must equal vector small b. So vector RP is vector RQ plus vector QP, and that's equal to vector small a plus vector small b. Now, Rx is twice XP. So vector Rx is 2/3 of the vector RP, which is 2/3 of A plus B. And now we can work out vector QX. Vector QX is vector QR plus vector Rx, which is minus A plus 2/3 of A plus B, and that's equal to minus A plus 2/3 of A plus 2/3 of B. We've simply multiplied out the bracket there. And then juggling the fractions, that's equal to minus 1/3 of A plus 2/3 of B. So that's QX found. And now we can turn our attention to vector XM. Vector XM is vector XR plus vector RS plus vector SM. That's the high road, remember? And all that comes to minus 2/3 of A plus B plus B plus a half of A. Multiplying that bracket out, we get minus 2/3 of A minus 2/3 of B plus a half of A. And again, juggling the fractions, that comes to minus 1/6 of A plus 1/3 of B. Now, comparing this answer with the answer for vector QX, we see that vector QX is exactly twice vector XM. And this is where a good facility with fractions comes in, of course. So we have proved that XM is parallel to QX, but they both pass through the point X, so Q, X and M must lie on a straight line. Now, you were probably so engrossed in following the algebra in this problem that you will almost certainly have missed something very powerful going on here. If this were a problem in geometry, we would probably be given some angles and the lengths of some sides and asked to prove some theorem or other. But all we were given was a simple parallelogram with no special properties at all. We were just told that M is the midpoint of the side SP and X is 2/3 of the way along RP. And using a bit of vector algebra, we have now proved that the points Q, X and M will always be in a straight line in any parallelogram, regardless of shape or size. It's so simple that it's very easy to miss the strength of the vector method. But I hope you'll begin to realise how powerful the vector methods of proof can be.